Well, we continue with tensor product. It's time to use the same techniques. I mean, the universal property that I explained before the break, to obtain many interesting further properties of tensor product. Here is one of them, corollary. Let U1, U2, and V1, V2 be vector spaces, and two linear mapping S defined from U1 to V1, and the other one, call it T, from U2 to V2, both of them be linear. Then there is a unique map. Then there is a unique linear map. And let's call it L now, from U1 tensor U2 to V1 tensor V2, such that L of U1 tensor U2 is equal to, well, U1 is here, is mapped by S to V1, and U2 is there, is mapped by T to V2. So S of U1 tensor T of U2. And well, this is an element of V1 tensor V2. Again, if such a map exists, since this element create the space, the span of them is the tensor product U1 tensor V2. If L is well defined, it is unique. So the main question is that why is this well defined? And the trick is the same trick that we applied before. But since we have the universal property, we don't need to go into all details, just consider B from U1 Cartesian product, but not tensor product. Cartesian product U1, U2 into V1 tensor V2, defined by this. This is well defined. B of U1, U2, and an arbitrary element of this, we define to be S of U1, tensor product T of U2. This is well defined, absolutely. Absolutely no problem here. And where do I use the fact that S and T, both of them are linear? They are reflected here. S and T linear implies that B is bilinear. So you have a bilinear map from U Cartesian product, U1 Cartesian product U2 into a space. This is our space W. And by the universal property. So therefore, by the universal property, B tilde is well defined. It's well defined. And note that B tilde was from U1 tensor U2 to V1 tensor V2, which is our W. And B tilde is the same thing that we call L in the announcement of theory. So that's the end of proof and notation. We write S tensor T for L. So in other words, if S is defined from U1 up to V1, and T is defined from U2 up to V2, then S tensor T is defined from U1 tensor U2 to V1 tensor V2, and it maps the element little u1 tensor little u2 to the map of the first element S of u1 tensor map of the second element T of u2. Special case. That special case happens a lot in function spaces. What if V1 is equal to V2 is equal C? So in this case, we need to understand what is C tensor C. And well, each element, what is a basic element? The basic element U times V, when U is in C and V is in C, we can write it, because they are scalar, we can write it as UV times 1 tensor 1. So and when we add them up with different scalars, every X, for every X in C tensor C, X has the general representation J from 1 up to N Uj tensor Vj, but it will be J from 1 to N Uj Vj, because these are scalars, 1 tensor 1. So at the end of the day is a lambda times an element 1 tensor 1. And now we can forget about this and say that this is usually done in all books, say that C tensor C is the same as C. This is equivalent to say that every element has this representation, but then we forget about 1 tensor 1. It has nothing to do with, it doesn't do anything, it's just a notation which is there. So keeping this, we can call it convention. So keeping this convention in mind, if you have S from U1, capital U1, to C, functional, linear functional, and T also from U2 to C, then S tensor T would be a linear functional from U1 tensor U2 to C tensor C, which we write C. So it will be another linear functional. And the definition is such that S tensor T acting on the basic element U1 tensor U2, I should write S of U1 tensor S of U2, but based on the above convention, I just write S of U1 times T of U2. So that's one special but important case. Another property of this, which indeed I will need in the next session of the book, is the Hamel basis for U tensor V. And here is the theorem, so for Hamel basis. Theorem. So U and V are vector spaces with Hamel basis E and F. And then this set, which is, when we can say E tensor F, but more explicitly then E tensor F when E runs over capital E and F runs over capital F. This is a basis, or is a Hamel basis for U tensor V. What we have done up to now, based on what we discussed up to now, we know that this set spans the whole space. So the question is for being independent. So proof that span, I mean, let me call this, there's no notation for that. Let me call it A. That the span of A is equal to U tensor V is, well, I say trivial. Trivial for us because we have discussed a lot about it. The question is about being independent. So assume that some j from 1 up to n, lambda j, and now we need to add lambda j because we did not consider all U tensor V. We just considered E tensor F with a collection of E and collection of F, not all of them. So lambda j is needed here. Lambda j, EJ tensor Fj is equal to 0. And our goal, where lambda j is in C and EJ is in E, Fj is in F.
Don't you need different indices on the E's and the F's here?
I explained this because we need to be careful here. You mean I write EIFJ?
Yes.
That's one way to do it. Another way, which is based on the comment, there is repetition is possible among EJ or FJ. For example, we might have, as Sheldon mentioned, we might have something like this. Say E times, well, how can I write such that? Oh, I use F prime. EF one element, E times F prime another element, and E prime times f prime. These are three different elements, but you see at the with my notation, this is E1 tensor F1, this is E2 tensor F2, and this is E3 tensor F3. And I multiply this by lambda 1, lambda 2, and this one by lambda 3. So it is possible that, for example, E1 be equal to E2 and be the same element. The way I wrote it, I just assume that E is in capital E and F is in capital F. And the same here.
Okay, thank you.
You're welcome. So EI is in EFJ. Oh, EJ is in E, FJ is in F, but we might have some repetition. And the way to do it is based on what we did before. I mean, the tensor product of two linear mapping. So we know that since E is a Hamel basis for U, there is a mapping phi from U to C such that phi at point E1 is equal to 0 and equal to 1. At this element is equal to 1, and phi at, here is the problem when I write EJ equal to 0 for J not equal to 1. There is a reason here I didn't write for J between 2 and N. There is a notation problem, I agree. I have to think what is the right way to do it. What I mean here, there is a phi such that at point E, for example, here is equal to 1, and at point E prime is equal to 0, and at all other points of the basis. We can put it this way. I know how to do it now. Phi of E is equal to 0 for all E is in E except E1. I think that works now. And similarly for F1, F is a Hamel basis for V. Therefore, there is psi from V to C such that psi of F1 is equal to 1 and psi of F equal to 0 for any F in our set except the one we chose before, except F1. And now, consider phi tensor psi from U tensor V to C. What can we say about phi tensor psi for any element of the form, I mean, U tensor V? By definition, this is phi of U, psi of V. That's by definition. Therefore, phi tensor psi of E1 tensor F1 is equal to phi of E1 psi of F1, which is equal to 1. And for any other element, for any E and F, such that either E not equal to E1 or F not equal to F1. Phi tensor psi at point E tensor F is phi of E psi of F. And then one of these is equal to 0. So either this is equal to 0 or this one is equal to 0. So one of them is 0, so it's equal to 0, the mapping. And now we apply it here. We apply it precisely there. We apply phi tensor psi to this sum. So therefore, phi tensor psi of sum equal to 0, and this is equal to, I forgot lambda j, sum j from 1 up to n, lambda j, phi tensor psi ej tensor fj. And this sum is again equal to, the first one is lambda 1 times 1, and for the rest, by the property we saw here, the rest is 0. So the conclusion is that lambda 1 is equal to 0. And we continue the same property, the same form of reasoning that I, so similarly, lambda 2, lambda n is equal to n, so they are independent. And we are done. So if you have Hamel bases of the ambient spaces, then you tensor product them, you obtain a Hamel basis for the whole product. And immediately from this corollary, before corollary, recall that the dimension of U Cartesian product V is the dimension of U plus the dimension of V. And now corollary immediately tells us that the dimension of U tensor product V is the dimension of U times the dimension of V. So somehow it's a bigger space. Then this is done. U1. And well, I wrote this as a corollary, but I mean, let me leave it as a simple exercise for the student exercise. U and V vector spaces. And just we assume that the second component, V1 up to Vn, are linearly independent. So we assume that V1 up to Vn linearly independent. And X, but don't assume that sum J from 1 to N, Uj tensor Vj is equal to 0. That's the consequence of independency. In general, if we have a summation like this equal to 0, we cannot say anything more. I mean, just the linear combination is 0. But now, thanks to this property, we can conclude that then U1 equal to U2 to UN equal to 0. Of course, the other way around is trivial. So that is another advantage of working with independent sets. Another observation after this, and that's really interesting when we go to functional spaces, assume that V is equal to Cn. Then what is U tensor product V or U tensor product Cn? Well, we know that Cn is the span of the canonical product E1 up to En. The canonical basis, I'm sorry. Ej, all of the components are 0 except the j's element, which is equal to 1. And therefore, every element based on the previous exercise, every element of this, every x in this space has a unique representation of this form, x equal to U1 tensor E1 plus UN tensor En. Because first of all, it spans the space, so it has to be of this form. And second, independency gives us the uniqueness. This is not quite a vector of dimension n, but we can use this to say that we have a mapping from U tensor Cn to Un, Cartesian product of U n times, which maps the element some j from 1 up to n Uj tensor Ej to the element U1 up to Un. We succeed here because of the uniqueness. We have a unique representation, so we can do this map. And we obtain this correspondence. This is a bijective map. Or in technical terms, we can say, if you want to use the technical terms, U tensor Cn is isometric. I think it's better to say isomorphic because there is no topology involved. Now, isomorphic to UN. And well, sometimes we abuse the notation and simply write U tensor Cn is equal to UN. But equality is, I mean, the way I explained about. even more in infinite dimensional case, and you need to be a bit careful here when a topology come into picture, when they can see the U tensor product L2. Well, we know that L2 is also spanned by E1, E2. So every element here, any X in U tensor L2 can be represented uniquely as the sum J from 1 up to infinity these times, Uj tensor Ej. True. And this is equal, but equality in the sense I explained above, the vector U1, U2, and so on. Indeed, it's not equality, it's isomorphic to that. And that is why they write, I mean, we can say that U tensor L2 is equal to U Cartesian U infinitely many times, or if you want Pj from 1 up to infinity, well, Uj, when Uj is equal to U. Up to here, there is no problem, but when we put a topology on this, for example, when we put a NOR, it's not for all elements of the product. We have some restrictions. For example, one of the restrictions that we will see before, I mean, we will not see in this my mini course, but you will see it next week when Michael Hartz talks about the very Arison space. Not all elements here, the elements which satisfy the norm of Uj squared is less than infinity. That's the meaning of U tensor G. But why do we have this isomorphism is based on the theorem we had above. Final comment about this, which is also interesting, is this one. Assume that L, a mapping from U to V is given. And then consider the identity mapping, so I, from space Cn into Cn, so identity. As before, but before we had map T, map S, and we form S tensor T. Now we form L tensor I from U tensor Cn to V tensor Cn. Right? Precisely as before. And how did it work? It mapped an element here to element here with the operation of this. What is an element of U tensor Cn? Well, we saw that for an element here, we can write U1, U2 up to UN. But if you want to be very specific and more precise, it's indeed U1 tensor E1 plus U2 tensor E2 plus UN tensor En, but we write it in this way. And what is the mapping? On the first component, L applies, and on the second component, E1 up to En, I applies, but I is the identity. So this is mapped to the element L of U1 tensor E1 plus LE2 E2, LU2 tensor E2 up to LUN tensor En. And again, we write this as L of U1, L of U2, L of UN. So it's a mapping we can now forget about tensor and say that we have a mapping L or I mean L tilde if you call, or stick to the same notation that we had before, from UN to VN, which maps this element to this element. I mentioned this because, as I said, for sure next week you will see several occasions when I mean the speaker will talk about consider well Hilbert space or Hardy space H2, and then they consider Hardy space H2 tensor L2 or Hardy space H2 tensor CN. You will see incidences like this, and that's the preparation for next week. To finish this part, I mean, up to here, it was based on my note. There is one proposition in the book, proposition 4.9. Well, up to here, I consider Hilbert vector spaces. When we go into inner product spaces, so let me add this. I need to say this before the proposition. Inner vector spaces. You have U, and there is an inner product in U, and the same for V. You have V, and there is an inner product in V. Sometimes to distinguish, I put a U here and put a V there. And then you form the tensor product U and V. And the question is that if you consider two basic elements here, say U1 tensor V1 and U2 tensor V2, can we define an inner product here? Well, the natural choice which comes to your mind is this one. We define the inner product, and that's the definition, to be the inner product of U1 and U2 in U times the inner product of V1 and V2 in V. The same problem that we had before shows its face. Why is this well defined? Probably in this format, it is not clear why we have a problem, but again, how do you define the inner product of two arbitrary elements, X and Y, when X and Y are in a U tensor V? To do this, well, X has a representation. The same for Y. And for X inner product V, you can write J from 1 up to N Uj tensor Vj, and for Y, I from 1 up to N I prime. Use the linearity, that's the way we define it. We take this out. I from 1 up to M, I think I wrote about M. And then you end up with basic elements. And now apply the definition above. Uj with ui prime and Vj with Vi prime. This happens in U, this happens in V. All the operation is correct. The only problem is that this is not unique. We have seen this problem before. This representation is not unique. X might have other representation, but Y at the end of the day, doesn't matter which representation we use, we always obtain the same number. There is no problem. So there is no problem, and our definition is okay. Why is this the case? And I think you know how to deal with this now. I mean, we have had several incidences. You can use the universal mapping property, or forget about universal mapping property, which means that forgetting about the proof of the universal mapping property. You define this on the scalar product, on the Cartesian product of U and V, and then obtain the null space. And I mean, you know how to do it. I've done it at least twice today and show that if we go to the quotient space, this is well defined. So it's not clear at the beginning, but at the end, it is well defined. One important property that it's explained in the book, and it connects to the topic before that section, the Shor product. Note that there are several steps to be taken here. One step, I just gave you the hint and I asked you to follow it. Why is this well defined? I didn't go into detail, but I told you how to do it. Now assume that it is well defined. Why is this an inner product? We have four properties to investigate. The first one is to explore the linearity. That's in the definition. I mean, we define it that way. Linear with respect to the first component, conjugate linear with respect to the second component. That is clear, no problem. The main difficulty is in this one. Why x and x is positive for, and why if x and x is equal to 0, this implies that x equal to 0. Why? These, to answer to these two questions, we need short product and explain a little bit. What is x? I mean, it has a representation like this, some j from 1 up to n, uj, vj. And let's see what is x times x. So j from 1 to n, yeah, so I from 1 to n, it's the same thing, ui times vi. By linearity, it's uj vj and ui tensor vi, and by definition this is uj ui times vj vi. Does this product tells you something? And why is this positive? Temporarily forget about, say, Vj, Vi. Just consider some j from 1 up to n, some I from 1 to n, uj inner product ui. This is the same thing as we call this vector Gramian vector. Gramian of u1 up to un is the matrix whose elements are inner product of ui and uj. Now the order is reverse, is uj and un, so it's Gramian transpose. That really doesn't matter. So it's Gramian, if you want, transpose here, applied on the vector eta inner product with eta, where eta is the vector 1, 1 up to 1. All the components are 1. In the general, when you put a vector with component eta 1, eta 2, eta n, here we have eta I, eta j bar, or bar or the other one. I mean, it depends how we write it. But here eta I is equal to 1 and you do not see it. So it's G transpose eta inner product with eta, and we know G is positive. So it's G transpose is also so positive. So this is positive. And the same thing, so this is one thing, exactly by the same reasoning, the sum J from 1, what was that, Vj, Vi. Vj, Vi, it's, I call this Gramian of U, it's Gramian of V transpose eta and eta, which is bigger than or equal to 0. So you have, let me write Gramian of V2. Vi, Vj. Both of them are n by n matrices. That's another reasoning. So back to here. Why this combination is bigger than or is equal to 0? Well, look at this and look at this. You have two matrices. Both of them are positive. Shor theorem by Shor. We know that ui vj, ui uj, and vi inner product vj, just component by component we multiply, is bigger than or equal to 0. And let's call this G. And this is nothing but, this is nothing but G eta and eta, maybe G transpose. Yeah, G transpose eta and eta, which is bigger than or equal to 0. Absolutely not obvious if we forget about the Shor product. So it's the Shor product which tells us that what we had a question to answer. We had a question to answer. Yeah, That's the short. By short theorem, we can show that the inner product of x and x is bigger than or equal to 0. Also, again, by the same theorem, we can answer this. Instead of answering this, I do this. If x is not equal to 0, then inner product of x and x is strictly bigger than 0. We can show this. And this is hidden here. If x is not equal to 0, then go back there. The representation was, I used the representation for x. Here is the representation I use. You remember we had before the break, there is a representation in which n is minimal. And when n is minimal, uj's are independent and vj are independent. I use it here. So I use n minimal, which implies that uj tensor vj, which is u1 up to un independent, and the same for v1 up to vn. We had this before. Consequence of that, when they are independent, g, the gramion of u, will be strictly positive, and the same for the gramion of v, strictly positive. And the theorem of Shor, we show that if you have two matrices both strictly positive, then g of, let me call it uv, will be strictly positive. Did I call it GUV here? I simply call it G, but you can call it GUV. GUV is strictly positive, and this is the same thing as, this implies that if you can see the inner product of x and x, it's nothing but GUV transpose of eta with eta, and that will be strictly positive. Done. So you see everything comes together very neatly here. And we can show by using techniques from tensor product and techniques from the short theorem to show that the inner product is well defined here, and we have an inner product space. Be careful before the next break. If you start with two Hilbert space, H1 and H2, of course you can form H1 tensor H2 as inner product spaces, the way defined above. But this is not necessarily complete. It's an inner product, not necessarily complete, even though H1 and H2 are complete. But we can do the completion. And the completion is also denoted by H1 tensor H2. So this is something, doesn't cause any problem, but sometimes we need to be careful about this. Well, let's have another break. We have covered all the